Good morning, students.
Good morning, ma'am.
Can you see the screen?
Good morning.
Yes, ma'am.
Yes, ma'am.
And whether my voice is audible properly?
Yes, ma'am.
Okay. So, in today's section, we are going to see metrics and norms, metric space and norm linear space. Already you might have familiar with definitions in your BSc classes, but still we will revise it. Okay. So, can anybody recall the definition of metric space? Fine. Okay, no problem. So, metric space. Metric space. First, we will define this. So, let M be a non-empty set. Non-empty set. A function D from M cross M to R is said to be metric on M if it satisfies the following conditions. So can you recall the at least conditions? What is the first condition? Distance of xy is always greater than equal to 0 for every xy belongs to M. What is second condition? Distance of xy is equal to 0 if and only if x is equal to y. These two also you can club or you can write it separately, no problem. I am writing separately. What is third one? Distance between xi is same as distance between yx for every xy belongs to M. And what is fourth one? Triangle inequality.
Triangle inequality.
Distance of xy is less than equal to distance of xz plus distance of zy for every x, y, comma z belongs to M. So this D is called as a metric function. Okay, this D is called as a metric on M, and a set together with this D is called as metric space. The set or the pair, we can say, the pair M with this distance function is called a metric space. Right?
Yes, ma'am.
So you take M as any non-empty set. Then if you can able to define a function D whose domain is M cross M and codomain is usually R plus, we can write, or R also if we write, no problem, because distance is always greater than equal to 0. Right? So then it is said to be metric on M if it satisfies these conditions. So we know that distance is always greater than equal to 0 and distance of xy is equal to 0 if and only if that point is, means that 2 points are same. And distance of xy is equal to distance of yx. What is this property called? What is the name? Symmetry. And this is fourth one is distance of xy is always less than equal to distance of xz plus distance of zy for all x, y, z belongs to M. That D is called as this D function is called as a metric on M, and M together with this metric is called as a metric space. Is that okay?
Yes, ma'am.
Okay. So can you give examples? For example, R with modulus. Okay. R with our usual metric. This is called as a usual metric. Modulus is a metric space. This you can write one. Second, every set M admits a metric. Admits a metric D from M cross M to R defined by distance of xy is equal to 0 if x is equal to y and 1 if x is not equal to y. What is this metric called as? What is this metric called as? It is called as a discrete metric. The above metric is called as discrete metric. Discrete metric. And M with this discrete metric is called discrete metric space. Discrete metric space. Is that okay?
Yes, ma'am.
Discrete metric and discrete metric space. Many times for counter examples and examples we will use this discrete metric space. Okay, so at the time you have to know what is that discrete metric. Can you prove this? Whatever D I have defined, it satisfies metric properties.
Yes, ma'am.
Because first property is always greater than equal to 0. Distance of xy is always greater than equal to 0 by definition only.
Yes, ma'am.
Yeah. If x is equal to y, again it is 0. And what is symmetric? Distance of xy is equal to distance of yx also it satisfies. Only triangle inequality you have to prove. In triangle also, you take any distance of xz plus distance of zy. If x is equal to y is equal to z, then 0 plus 0. Yes. So I think you can easily prove this. I will give this as exercise or prove. You can take exercise. Prove that D is a metric on M. This D is a metric. Now we can have next example. Third example. Define D from R cross R to R by distance of xy is equal to modulus of x minus y. Then D is a metric on R and is said to be usual metric and is called a usual metric on R. This also you can easily prove. This modulus of x minus y is called as a usual metric on R. Is that okay?
Yes, ma'am.
Yes, ma'am.
Fourth example, we can have define d from 0 infinity to cross to 0 infinity to r by distance of xy is equal to 1 upon x minus 1 upon y. This also is a metric on 0 comma infinity. This also you can prove.
Yes, ma'am.
0 is not included in this set. So 1 by x, 1 by y are well defined. Is that okay?
Yes, ma'am. Yes, ma'am.
So this is also a metric on 0, open interval 0 to infinity. Fifth one, if D is a metric on M, then show that now with if we are having one metric on M, then we can have we can construct another metric with using this D. So we will prove that, or you can also easily prove. Then show that first one, row of xy is equal to under root of distance of xy. Second, I will define as sigma of xy is equal to, say, d of xy upon 1 plus d of xy. And third term of xy is equal to, say, minimum of distance of xy comma 1. These are metrics on M. This we want to prove. So can you try this? So you can take this as homework. This all things you might have did in your BSc, just we are recalling for our further purpose. Is that okay?
Yes, ma'am.
Rho of D is already a metric, and we have to prove rho of xy is equal to under root of t of xy. Then another metric we are defining as d of xy divided by 1 plus d of xy. And third one we are defining as minimum of d of xy comma 1. This all three forms a metric on M. So we will get 4 different metrics. 4 म्हणजे one is original D, and then using that D we are defining different 3 metrics on M. Right?
Yes, ma'am.
Okay. So this also you. Now we will define normed vector space. Actually, we are going to take a guest lecture on this, so I am not going in details of these things. But for my next lecture, I will require metric space and all that things, so I am defining this. Okay. So in guest lecture, one of the faculty from other university will introduce you metric space, norm linear space, and some of the topics. Okay. So we will just quickly define normed vector space. So everybody familiar with vector space?
Yes, ma'am.
Linear algebra, vector space. In linear algebra, you might be familiar with vector space.
Yes, ma'am.
What is vector
Yes, ma'am.
space? Students, are you there?
Yes, ma'am.
Yeah, so please respond. What is vector space? Let V be a vector space over the field F. A function we denote it like this, a function from V to R, a function, this is the notation for norm from V to R is said to be norm on V if it satisfies the following properties. Following property or following, we can write one, which it should satisfy. Norm of x is always greater than equal to 0 for every x in V. Second one, norm of x is equal to 0 if and only if x is equal to 0. Third one, norm of alpha times x is equal to mod alpha times norm x for all x is in V, and where that alpha belongs to? Alpha belongs to F field. And fourth one, norm of x plus y is less than equal to norm of x plus norm of y for every xy belongs to V. And that V together with this norm is called as a vector space. Then V together with this function is called a vector space. Sorry, normed vector space. Normed vector space. Is that okay?
Yes, ma'am.
I just define metric space, norm, and norm vector space. So we'll just quickly give examples. Norm from R cross, not R cross, R to R, and define norm of x is equal to mod x. Then R together with this norm is a normed vector space. It is a vector space is also called as a norm linear space. Okay, I will write here only. Norm vector space or normed linear space is one and the same. Linear space, vector space is same. Normed vector space or normed linear space. We will use this short form n dot l dot s NLS. Okay, non-linear space. Okay, we'll define another example. It is first example. Second example. On Rn, we will define a norm. What is Rn? The space of all n tuples, right?
Yes, ma'am.
Yes, ma'am.
How the elements of Rn looks like?
X1, X2 up to Xn.
x1, x2, xn. Set of all x1, x2 up to xn. Where this xi belongs to where? Xi belongs to
R.
R
R.
for every R. So this space is called as Rn, or the space of all n tuples. Now we define a norm on this. Define the maps. Say first one is norm x1. I am defining as summation I is equal to 1 to n mod of xi. Second, I will define as summation I is equal to 1 to n mod of xi square raised to half. And third, I will define as maximum norm. We denote it as norm infinity. Maximum 1 less than equal to I less than equal to n mod of xi. Then this norm, this one norm, two norm, and infinity norm, these functions are nothing but norms on Rn. That also we can easily show. Okay, you can take this as again exercise. We can easily prove that this function satisfies the properties of norm. Whatever we have 1, 2, 3, 4 we have written here. Is that okay?
Yes, ma'am.
Whether you are listening
Yes,
this
ma'am.
first time or already familiar with norm definition. Are you listening this norm definition first time?
No, ma'am.
No, ma'am.
Yeah, I'm just recalling this because we will require this in further discussion. Okay, now we will define LP space. LP space. What is LP space? For 1 less than equal to p less than infinity, define LP space as the space of all real sequences x is nothing but xn, n is equal to 1 to infinity, such that summation I is equal to 1 to infinity mod of xi raised to p is finite. That is LP I can write as a space set of all x, or we can say sequences xn, such that summation I is equal to 1 to n mod of xi raised to p is less than infinity. That is x belongs to LP if and only if summation I is equal to 1 to n mod of xi raised to p is finite. Okay, so what is LP space? LP space is nothing but the space of all real sequences. Real sequences, but how are the sequences? Summation for which summation I is equal to 1 to infinity mod of xi raised to p is finite. Okay, so such space is called as a LP space. Now we define a norm on this. Define norm will denote as a peak norm on LP as norm of xp summation I is equal to 1 to n mod of xi raised to p raised to 1 by p raised to 1 by p. This is nothing but a norm on LP space. So when p is equal to 2, it will become L2 space. If p is equal to 1, that will be nothing but L1 space. Okay. L infinity space. Actually here p is equal to infinity, then this reduces to maximum, that p will define it as maximum norm. We will write over here example. Show that L1 together with one norm is a normed vector space. Normed linear space or vector space. What is L1 norm here? L1 with norm 1 or whatever above norm are there, we can L1 norm, L2 norm. What is L1?
Norm F1.
L1 is nothing but the space of all x such that sequences such that summation I is equal to 1 to n mod of xi is finite. If I take L2, what is L2 space? X is equal to set of all real sequences such that summation I is equal to 1 to n mod of xi square is finite. Okay. Now we want to show these are the, this one is a norm . So can you show this L1 norm? Which properties I have to prove?
No.
Alpha x.
Take alpha belongs to f mod of norm of alpha x. I want to show it is equal to mod of alpha. Okay, before norm, taking norm of alpha x, what is alpha x? What is x here? x1, x2, xn. What is alpha times x? What is alpha times x? Alpha x1, alpha x2, alpha xn. N tuple, right? So what is norm 1 of alpha x? What will be this? Summation I is equal to 1 to n. What will be this? Mod of alpha times xi. So So now summation I is equal to 1 to n. Alpha is scalar. So modulus property I can use. Xi is a vector. Mod alpha I can take outside. Summation I is equal to 1 to n mod of xi, and that is nothing but mod alpha times norm 1, right? And what is fourth property? Let x comma y belongs to L1. Then what is x plus y? It is nothing but x1 plus y1, x2 plus y2, comma xn plus yn. So what is norm of x plus y? One norm. What will be this? Summation I is equal to 1 to n mod of xi plus yi, right? So this now I can use modulus property. I is equal to 1 to n mod of xi plus mod of yi. Oh, sorry. Summation I can do. Plus summation I is equal to 1 to n. I can write this.
Yes, ma'am.
We can write one step also. In between we can write one step. Okay. For your understanding, we will write first like this. And then which is equal to summation I is equal to 1 to n mod of xi plus summation I is equal to 1 to n mod of yi, and that is nothing but my x1 norm plus 1. Is that right?
Yes,
ma'am.
Yes. So similarly, you can prove infinity norm and L2 norm also. So Rn together with this norm 1 is called as a L1 norm. Sorry, but for that sequence is it is a set of all, not Rn, but already we have defined it. Okay, not necessary to. Okay, LP space already we have defined. Not all n tuples, it will be. Is that okay? These are nothing but quickly revision of your definitions of metric space, vector space, normed vector space, some of the examples, and LP space. Okay.
Yes, ma'am. Yes, ma'am.
So in next lecture we can start closed sets and open sets, open and closed sets.
Okay, ma'am.
Is that okay?
Okay, ma'am.
yes. Yes,